This section is regarding a series of equations that you can use with thermochemistry, with electrochemistry, and with equilibrium. We're going to go through each of these various reactions and give you some specific details, and then separately there'll be a video regarding the various examples that you could practice with. It would be encouraged that you either try out those example problems on your own and then use that video to just check your work, and or use the video sort of in the background as you're trying out those problems. Okay? So here are the various reactions, some of which are listed in your green equation sheet, whereas others are not. Whoops, sorry about that. So you do want to check where your green sheet is and what kind of information is going to be provided. You'll also see that these equations are highly related. Anytime you see a K value or a Q value, they're going to be highly related to Le Chatelier's principle. So it's a nice review of all of the various concepts. All right, starting with the two reactions that are shown in one. As you know, delta G is really, while it's defined as Gibbs free energy, it actually represents the amount of work that you might be able to get. So keep in mind that when delta G is negative, you are getting a spontaneous reaction. That means that you are getting work out of the reaction. Somehow it's continuously reacting and you're then able to obtain work. You'll notice here that there are a couple of details. The Faraday's constant, letter F, is on your green sheet. And the E cell, this is going to be the standard voltage. So that's whatever voltage you're obtaining from your reduction table of voltages. And I know that because there's a little not symbol on it that represents the fact that it is standard. Let's go back to N. If you remember talking about balanced reactions of redox reactions, N represents the moles of electrons transferred. It's the number of electrons that you have canceled throughout that question. So as you balance the reaction, whether you do it by Mr. Seiler's way with half reactions, or you do it with my method of oxidation numbers, doesn't matter. The number of electrons that you end up canceling represents your N value. So that'll help you with this equation. It is very simply a plug and chug once you get the hang of what is what. The second equation, very similar, but is more related to the equilibrium constant. So there's some things that you need to remember. First off, in each of these equations, delta G is going to be provided as joules per mole. So you want to keep that in mind. Your R value, therefore, is going to be the 8.31. And we want that 8.31 because, again, it's joules over moles Kelvin. That may, of course, point out that temperature needs to be, of course, in Kelvin. And then finally, as you take the natural log of the K, keep in mind that this is not Kc, nor is it necessarily Kp. What it is it's the equilibrium constant, and it's the thermodynamic equilibrium constant. So as you do that, all of your pressures must be in atmospheres. So anything that is gaseous should be listed as a pressure in atmospheres. And all of your solutions must be listed as molarities. As you go through that and you watch for some of the things that are occurring, what is nice about Mr. Seiler's method is that you can see how this is being created by following those half reactions. And you can also create a Gibbs free energy for just a half of a reaction to know just how much that particular reaction might give when it is combined with another half. When you take these two reactions, which you can see is that you can manipulate by setting these two things equal, manipulate one calculated equation. So you are deriving this equation by merging the two above. Again, if you're comfortable with that idea, it is just a matter of plugging and chugging as you get a sense of the various variables. At this point, we have a couple of things now that we're thinking about. And that really boils into one equation that we did not do much with, and that is number 3, and one equation that we're now going to do a lot with, and that is number 4. If you remember from number 3, this equation was shown to you in the midst of working with the thermodynamic data table. And as you were working with thermodynamics, we pointed out the difference between delta G and then separately that of delta G naught. So let's revisit that. Delta G naught is again the standard Gibbs free energy. It's what you might consider your theoretical. And there are, of course, a number of standards that are out there. The one that we are currently using is the one for 25 degrees Celsius. But when we make those calculations, we're assuming that the gaseous particles are working the way that they are with respect to their chaos, as well as the enthalpy heat is being released according to that temperature. So these standards, again, are based on 25 degrees Celsius, 1 atmosphere, and what you're going to see is it's also based on the 1 atmosphere of gaseous pressure for every partial pressure, as well as 1 molarity for every single aqueous solution. The delta G, without the naught symbol, is what we would consider the experimental. What are we seeing in the moment right as the reaction is taking place? And that's why we have a Q. So again, the value of K, your thermodynamic equilibrium constant, is going to represent what we're expecting to see. When that value of K is very large, we're expecting the reaction will go in a very, not necessarily quick, but it will definitely make a ton of products. Q is what do you have right there in the moment. So maybe it's the concentrations that you were able to work with as initial concentrations. Maybe it was you want to know which direction it's going to shift. So those initial concentrations, whatever the case may be, Q is your experimental, what is occurring right now as you're mixing the chemicals together. Having said that, the Nernst equation provides you with a similar calculation, only the calculation is meant to actually go through the voltage. So rather than looking at how much work you might get out of it, you're looking now at what kind of voltage are you getting out of it. So one more time, E naught is going to be the value of the cell. It's theoretical and it's coming from the standards that are on the table. You could run the Nernst equation for a half cell, in which case you would be listing just the reduction or just the oxidation voltage. E cell, without the naught symbol, is again the experimental value. So as you looked at experiment 36, one of the problems with experiment 36 is that we should have been running each of those reactions with 1 molar concentrations. Instead, however, we were using 0.1 molar concentrations, which is automatically going to change your experimental voltage compared to your theoretical voltage for some of those reactions. Not all of them, but definitely for some of them. The variables that you now see next to the natural log are the same ones as above. R needs to be 8.31 in joules per mole Kelvin. Temperature will be whatever temperature you are actually using, and again, that's a realistic value. So while we're considering the theoretical, comparing it against 25 degrees Celsius, this temperature needs to be the one at which you're at. N is going to be the number of electrons that are transferred. So as you balance your half reaction, as you balance your full redox reaction, it'll be the number of electrons that you see passed. Faraday's constant is again on your green sheet. And Q is going to be your thermodynamic equilibrium constant, but instead of plugging in equilibrium, it's going to be initial amounts. So what are you looking at in that moment? All right. For many people, they would prefer to minimize, and that's fine if you'd like to just plug in your Faraday's constant, your value of temperature, and your R. If you want to substitute in and use that temperature as 25 degrees, which in many cases it's going to be, feel free to use this. I personally know that sometimes that temperature is going to change, so I prefer this one. Again, if this is not on your green sheet, it would be a great opportunity for you to plug it into your calculator. All right. As you can see below, we then have two equations that we've now already talked about. So this next video is going to go through the various examples that are using it. You'll see that that really takes up the remainder of the notes, except for electrochemical cells and some calculations there, which if you've taken physics should be review. So because of that, feel free in this next video to, again, either practice it on your own and just check your work, leave it in the background, and by all means, fast forward as you need.